In this video, I'm going to show you how you can use double integration with polar coordinates to work out the volume of a sphere of radius A. So in Cartesian form, we would have some sort of surface and then dx and then dy. But then when you convert it to polar form, we've already seen this. You somehow stick this r in here, and we've already justified why. But then you need to express the surface in terms of the radius and in terms of the angle, and we've already done this. So we've already done how to jump from here to here. The next step is to set up this thing here to represent our sphere. So a sphere in 3D is given by this. If you want to know the surface, which is what we want, the surface expressed in terms of the radius and the angle, make z the subject, because z tells you the height or the surface. So make z the subject. So take away x squared, y squared, and then square root it. So z squared equals a squared minus x squared minus y squared. And when you square root it, you get two versions, the positive version and the negative version. The positive version represents the top of the sphere. The negative version represents the bottom of the sphere. We don't care about the bottom one, so just ignore the negative version. So we know that this bit here is given by, so remember, half of a sphere, which is our v. Later on, right at the end, we're going to times it by 2 to get the whole sphere. But for the time being, v, which represents half of the sphere, is given by the double integral, and then we need to express the surface. Well, the surface was square root a squared minus x squared minus y squared, and then we need to stick this r in here, r d theta, and then because if you look at this, we need to work in terms of r first and then theta. So this thing here would mean we have to say r equals something, and the outer one would be theta equals something. So r, well, if you look at the domain, r, so remember, you're moving like this, and you're scanning through the angle from here all the way around here. So if you think about it, r starts from a radius of 0 to a radius of a. So r equals 0 to a. r0 to a radius of a. r of 0 to a radius of a. r of 0 to a radius of a. And you're scanning through, in terms of the angle, you're scanning through all the way from an angle of 0 to an angle of 2 pi. So this would be 0 to pi. So our v, which is half of a sphere, is given by this thing here. So our half of the sphere is given by this thing here. So now we need to convert everything in terms of r. We don't want to work in terms of x and y. So in terms of r and theta, we need to convert it into polar coordinates. So when you work with polar coordinates, you have to have this at the back of your mind. Always picture this: x equals this, y equals this, and this is very important. Whenever you see this, you can replace it with r squared. So this thing here, factor out the minus, so that would then be x squared plus y squared. So now we can put this r squared into here. So that would then give us this thing here. And let's move this r over here. So that will then give us this. So now looking at this you know it's easy. This you know is easy to integrate with respect to r, because this is near enough the derivative of this thing here. Because well, rather than using substitution, we're just going to integrate it directly, because we know it's going to be easy to integrate, because this thing here is near enough the exact derivative of this thing here. So anyway, let's integrate this. So when you come to integrate this, picture this in your mind. Well, you could use substitution, but train yourself to do all in one go. So so this is like the square root to the power of half. When you integrate it, it would be one notch higher. So that would be 3 over 2. So so picture this in your mind. When you differentiate this, it will then give you, so when you differentiate this, the power comes down, the bubble stays the same, the power gets minus by 1 times the derivative of the bubble itself, which will be this. If you tidy this up, it will then give you this. So notice that this is your square root thing, this is your square root thing, and then this is r here, this is r here. You just don't want this negative 3, so you would go back to your initial guess and then stick a negative a third in here, so that when you differentiate this, it will then give you this thing here. In short, if you integrate this, it will then give you this thing here. Okay, so use substitution if you want to, but train yourself to be able to integrate this all in one go. Okay, so now that we're here, remember r is from 0 to a, from 0 to a. So now when you put a into here, this whole thing here disappears, so therefore the whole thing disappears. Take away, put 0 into here. Remember, you got a minus, so it becomes a positive. Well, anyway, you put 0 into here, it will then give you this thing here. And then when you get this multiplied with this, it will just give you a to the power of 3. It will just give you, hang on, it would just give you a to the power of 3 over 3. So now remember, this is a constant, but we need to integrate it with respect to theta. So when you integrate this, it will be the constant theta from 0 to 2 pi. So now when you put 2 pi into here, it will then become this. And remember, this is just half of a sphere. So to get the whole sphere, you would times it by 2. Therefore, the volume of a sphere is given by this. Okay.